Everyone, welcome back to Deviations. Today we're going to be talking about continuity and limits at infinity. So what is continuity? So the general definition is that if we have the limit as x approaches a of f of x is equal to f of a, our function is continuous. And that's across the entire domain, or an interval. So here are some examples of continuous and discontinuous functions. We have a general polynomial here, and then we have a rational on the right. So the polynomial is continuous across its whole domain, but we need to be really exact when we're talking about continuity with these rational functions, especially because we have these gaping asymptotes obviously here, but this function is not defined at these points. So that means that it's continuous across its domain because its domain does not include these points. But if I said, is it continuous across the real domain, then it wouldn't be continuous across the real domain because these points are included in the real domain, even though they're not included in the function's domain. All right, so now we're going to talk about removable discontinuity. So here's an example. If I have f of x is equal to x squared plus 5x plus 6 over x cubed minus 3x squared minus 10x, I'm going to take the limit as x approaches negative 2. So if I try direct substitution, that's not going to work, so we're going to manipulate algebraically, and we are going to be able to cancel out common factors of x plus 2. And once I do that, I will find that the limit as x approaches negative 2 of f of x is equal to 1 over 14. So graphically, we can see what's going on. We have each little section of our rational function here. Not really concerned about the asymptotes because we're talking about a little hole denoted by the little white circle that is about to show up at negative 2. So with removable discontinuities, you can probably tell we can approximate very well the value of our limit because our function is approaching it very nicely. So we can approximate this with high accuracy to get 1/14. So that's a removable discontinuity. So jump discontinuities are really prevalent in piecewise functions. So here's an example of one of those. F of x is equal to x plus 3 given that x is less than or equal to negative 1, or 2 to the x given that x is greater than negative 1. So this exponential and this linear, those are continuous across their domains. So we probably don't need to worry about jump discontinuities there. But here at negative 1, that's where we need to worry about our discontinuities. So we are going to take the limit from both sides as x approaches negative 1, and then we'll see if they equal each other, and if they don't, then the limit doesn't exist. So if we take the limit from the negative side, we're going to get 2, and then from the positive side, we'll get 1/2. 2 does not equal 1/2, thus the limits are not equal, thus the limit does not exist. All right, so that's jump discontinuities, and here's our graph. So as you can see, there's our linear coming in there, and then our exponential. And right here, we have a jump. So the next type of discontinuity is the infinite discontinuity. This could also be called the asymptotic discontinuity. And with these, we need to be especially careful about how we define it. You'll see why in a second. So I'm going to ask specifically, is f of x equals 1 over x continuous on the real domain? So what we're going to do is we are going to find out where we're going to have an asymptote, and it's going to be at 0 for this general rational function. So we're going to take the limit from both sides, and negative infinity definitely doesn't equal positive infinity, so the limits do not equal each other, thus the limit does not exist. So here's our graph. Everybody should know what 1 over x looks like, but I'm just going to show it anyways. And if I'm defining it on the real domain, as I said at the beginning, this point is defined on the real domain, so it's discontinuous there. But if I was saying, is f of x equals 1 over x continuous on its own domain, and its own domain is just the real numbers if x does not equal 0, that means that it is continuous because 0 isn't defined. So 0 isn't part of the domain, so this function is continuous on its domain. So that's infinite discontinuities. Now we're going to talk about some continuity properties. These should seem pretty trivial, so given that f and g are continuous, we can do all the major operations with them. So now for the second part of our video, we are going to be talking about limits at infinity. We're going to begin this discussion with a review of horizontal asymptote rules. So if m is the degree of the numerator and n is the degree of the denominator, if m is less than n, then there is an asymptote on y equals 0. If m is greater than n, then there is no horizontal asymptote. And if m equals n, then we're going to divide by the leading coefficients to a value q such that the asymptote is y equals q. So a little bit more quantitatively, if I have a x to the m over bx to the n and m equals n, I'll just have an asymptote at y equals a over b. So those are our horizontal asymptote rules, and we will do an example now with a rational function. So if I have f of x is equal to 3x squared minus x minus 2 over 5x squared plus 4x plus 1, and I want to take the limit as x approaches infinity, what I'm going to do is I'm going to look at the degree of the numerator and the denominator, and I'm going to say that they are the same. So now what we are going to do is we are going to divide 3 by 5, and we are going to get 3/5, meaning that the limit as x approaches infinity of f of x is equal to 3/5. So we have just found the height of the horizontal asymptote, and we have found the limit. So that is limits at infinity. Next time we will be talking about differentiation. That's going to be a big unit, really exciting stuff coming up. Thanks for watching. Please like and subscribe. See you in a bit. Bye-bye.